All right, we're back. We're still on page 65, still doing compositions of trig and inverse trig functions, but instead of having a fixed ratio, we have a variable ratio in this case. So it's a little more complicated because we have to worry about the domain, but it's not that bad because if you've been dealing with these things and kind of like memorizing and internalizing, you sort of have an idea of what to do. Like we know we're going to draw a triangle. We know the domains of the inverse trig function, so that can help us here. So for example, if I'm going to do the inverse sine of something, so let's say the inverse sine of u, I know that u has to be between -1 and 1. U substitution, substituting u in for an ugly thing, is like one of the most common things that you'll be doing in math just forever. I mean, anything that looks weird, you immediately try making, if you see a bunch of weird things, you're like, maybe if I made that u, the whole problem would like look simpler, and then you do it. So get used to that. Here, u is x plus 3 over 2, so I know that, how am I going to write this? -1, x plus 3 over 2, and 1. So I'm going to multiply by 2, and then I will subtract 3 from everything, get -5 and -1. So this is the biggest possible domain that I could have. It could get smaller as I do the problem. Like I could lose, typically you either lose, I don't know if this is necessarily definitely true. You typically either lose the middle of the interval, which would be -3 in this case, or you lose the endpoints. Those are the two things that'll like go away when you pick up additional restrictions. So let's see if that happens. But that's the biggest domain I could possibly get. Now let's do the problem and see if anything happens. So draw this, and then we have a theta. So sine of theta is x plus 3, bad 3, x plus 3 over 2. So obviously this is too close. All right, too many things happening here. This is 2. I don't know where that went. And then this is too close to the next problem to be useful. So here's kind of a caveat for you, or a warning or something. When you're doing these problems, it doesn't benefit you to expand what's inside the radical if you get something that looks like this. So I'm going to get 4 minus the quantity x plus 3 squared. Look at that. I can tell that that's a missing side. I can tell the hypotenuse is 2. I can tell the leg is x plus 3. And I know that that's just the result of using the Pythagorean theorem, basically. If I expand that, it's going to just look like some garbage quadratic inside a radical. I lose all of the form, all of the usefulness. Don't overexpand. It drives me insane when students just start expanding everything. Like, don't expand. Like, then you lose kind of the nuance of the problem. So let's see. I need to find the secant of theta, which in this case is, so the cosine is the radical thing over 2, so this will be 2 over the radical thing. 4 minus the quantity, x plus 3 squared. And I pick up some restrictions, right? You cannot divide by 0. What would make the thing inside the radical equal 0? Well, it turns out, and this will always be the case when you're doing these, the thing that makes the thing into the values of x that make the, I don't know, the radicand, right? Is that the thing inside the radical? 0 are actually these values. This will always be the case. So we want to kick those. I mean, you can test it and see, like plug in -5, add 3, -2, square it, you get 4. 4 minus 4, 0. Do the same thing with -1. It's going to work. So our final answer is going to be secant of sine inverse of x plus 3 over 2 is actually equal to maybe I should move this over. I don't know. It's like I definitely don't have enough room, but I just flat out don't have enough room based on the way I'm writing it. Really, the problem is this arrow thing. Get out of there. All right, so this equals 2 over radical 4 minus quantity x plus 3 squared. The inspire will probably expand that. There's nothing we can do about that. And then the domain originally included -5 and 1, but we kicked it out because you cannot divide by 0. So this is our domain. So let's check that. I really don't know what the inspire is going to say the answer to this is. I think it's going to expand everything. I don't know. So I'm just going to do the secant of the arc sine of x plus 3 over 2. Let's see, expand. What do I want to do here? I want to complete the square. So complete the square is built in, but I just want to complete the square on like the thing here. Comma x, comma x. There you go. So it's really annoying that it does that, but it does. We could also ask the domain of this, comma x. Forgetting my x's. There you go. Gets it right. It's mind-boggling to me. It's amazing. Like, how is it doing that? I don't know what it's doing, because that seems like more advanced programming than the calculator seems to really have in it in a lot of cases. Although, who am I to judge? Computer algebra systems are amazing. All right, let's do one more problem. Inverse cosine. So cosine inverse of u would mean that I definitely need u to be stuck between -1 and 1. But u is 2x plus 1. So I need -1, 2x plus 1 over 5 less than or equal to 1. All right, so I'm like a piece at a time. So -1 times 5 is -5, minus 1 is -6, divided by 2 is -3. And then 1 times 5 is 5, minus 1 is 4, divided by 2 is 2. So there. All right, so that's the biggest domain we could possibly get. We might end up kicking out -1/2. We might, if that's if just x ends up in the denominator, we might end up kicking out -3 and 2, or we might keep everything. We'll find out when we draw a triangle and simplify. All right, so here's our theta, and cosine is 2x plus 1 over 5. So this, again, don't oversimplify. This will, well, you can simplify the 5 squared, 25. 25 minus the quantity 2x plus 1 squared. All right, and I need cotan. So therefore, the cotangent of the cosine inverse of 2x plus 1 over 5 equals cotangent. So the tangent is the radical thing over 2x plus 1. So this will be 2x plus 1 over the radical thing. Since the radical thing ends up in the denominator, we kick out those endpoints because they will make the denominator equal 0. So comma, what are you? 2 little weird dots, comma, -3x2. So we're always trying to think about the domain because you've got to make sure that it's working for you. So I think that that's our answer. I mean, I guess we could check it. So let's see. And then what are we going to do? Then I'm going to, I think, stop this video, come back in another video, and maybe do that other problem. Arc cosine of 2x plus 1 over 5. So we get this. It does the annoying thing again where it, I don't know, where's that 2 coming from? I do not know. Let's see. Let me just put in mind 2x plus 1 over the square root of 25 minus quantity 2x plus 1. This is another way to check your answer, just like type in yours. Factor -x squared minus x plus 6. Easier to do that in your head. We get that. So yes, we got it. How about the domain? Domain of this thing, comma x, dude. We get this, and then it's, why is it saying that? I think that's wrong. Let's see, if this is x equals -1/2. It's the arc cosine of, so it's the inverse cosine of 0, which, you know, is going to be pi over 2, and the cotangent of pi over 2 definitely exists. So that's another one. You get these weird, so this happened somewhere else with compositions. I don't remember where, but sometimes the domain thing does get it a little bit wrong, and it has something to do with like the weird things that it converts to, like in the interim, I think, like as it's tracking it. I don't really know, but so like always be on the lookout, right? We did it by hand. We're confident by hand, and then it gave me an additional restriction, and you saw what I did. I tested it like a piece at a time, and it worked. So that restriction should not exist, even though the calculator claims it will. So I'm gonna stop this here, come back in the next video, and in the next video, we are gonna try to simplify this by hand. And that seems like it's gonna go really well. So we'll see. But anyway, I will see you there when we try to tackle that. So till the next video.